Okay, good evening. So my name is Alexei, and this is my colleague Pasha. We will talk about machine learning and data merging in H2O driverless AI with data table. So H2O driverless AI is a pretty complicated tool and very powerful. So this tool is designed to automate machine learning. It's doing automatic visualization, automatic feature engineering, many interesting things. And one of the tools that is behind this powerful product is H2O data table that powers data merging, machine learning, and visualization in driverless AI, and also provides many other critical capabilities. So here is a roadmap for H2O driverless AI. You see how complicated this tool is, but data table actually is involved in most of the items on this chart, like automatic visualization, FTRL models, and some transformers for bring your own recipe, and many others. So what exactly data table is doing in driverless AI? So here is a list of things. It's mostly doing data merging and also got some models. So for data merging, data table is doing reading and writing CSV files and binary files. It's doing multi-column sorting and grouping operations, filtering. You see stats calculation for columns, target encoding, doing frame joining and appending. So recently we started adding some models to data table so that it can provide some high performance capabilities in terms of modeling that are lacking from the standard packages. So you see data table starts doing FTRL. FTRL stands for follow the regularized leader. So this is the online learning algo that we recently got into data table. So it's doing binomial, multinomial, and numeric regressions. We also got fast one-pass data aggregator so that we can aggregate gigabytes of data for automatic visualization in driverless. We have a parallel randomized k-fold splitting in data table for k-fold split. So I would like to talk a little bit about the FTRL algo here, just to provide you some details, what kind of modeling capabilities data table is doing, and then Pasha will talk about core data table capabilities in terms of data merging. So a little bit about machine learning with data table. You see some people on Kaggle saying that data table is doing very good on big data sets, like 9 million of rows could be processed with our implementation of FTRL algo in just 7 seconds. And people are really happy because they can read large big data and do at the same time with data table, at the same time they can do learning with data table. And why people are so happy? That's because FTRL is pretty powerful algo designed by several Google folks. So it can, originally this paper was published and it explained how FTRL algo could be used for binomial classification. And we did our own implementation of FTRL. So it's using, there is a Python front end, of course, because data table is basically a Python package. There is a C++ backend. So it's parallelized with our own in-house thread pool, and we are using hog-wild approach. This is what is making it so fast. So it supports Boolean, integer, real, and string features. We also use a hashing trick based on more hash function, so it's pretty fast and provides reasonable number of hash collisions. So you can also do arbitrary order feature interactions. So if you see some features are important, some features are not, you can mix this all together, and you can do second order, third order, or any other order of feature interactions. This is what makes it pretty accurate. And we went a little bit further in terms of the scope of this paper. So we also added multinomial classification and regression for continuous targets based on the same FTRL approach that was presented here. So a little bit about details, how you would like to use it. So here is a sample Python code. So you see, we just import data table, we import data table models, we read CSV file with data table. This is a parallel read, so it's pretty fast. We define training data, target column, and then we create FTRL object. So basically, there is a set of default parameters for FTRL algo in data table. Here we just change the learning rate to 0.1 and number of bins for Hessian trick 10 to 6. Then we do fit. You can get access to feature importances, and then you just do predict. So this is all done with data table. There is no other packages involved here, and this is all pretty fast. So if you want to learn a little bit about data table FTRL capability, data table modeling capabilities, you can go to the help page to read the docs and check it out. Just to summarize, 5 reasons why you want to use machine learning capabilities from data table. That's because, first, it is reliable, because now it is integrated into our main product, H2O driverless AI, and was tested and demonstrated a pretty accurate result and pretty fast. You see, it can process 1 million rows in seconds, because Hessian trick that we implemented is pretty fast. It is fully parallel, and this is what makes it a very interesting approach in terms of FTRL. So it's all data table. You read data, manage data, fit, predict, save results with just data table. It's already on Kaggle, so if you are into Kaggle things, you can check out this kernel that was prepared by our Kaggle grandmaster, Bojan Tungus. And I see many people are using this kernel. And the last but not least is that data table is open source. So if you don't like something in this particular implementation, you can adjust it, or you can take a look how this particular algo was implemented. So we're not hiding anything from the user. Yeah.
But this in Kaggle is not. It's not H2O. It's not S2O product, right?
It's open source and it's developed by H2O folks, but it's on GitHub, so it's not commercial. Yeah, so it's open source. Yeah.
It's used by Kaggle, right?
I guess it's anyone can go to Kaggle and use it. Anyone can go just do pip install, as you see, and use it. Anyone can go to GitHub, access the code, check out the implementation, or make a PR for improving something, or just open in a ticket saying, okay, guys, I don't like this particular thing, or I would like a new feature to be implemented. So it's fully open to the community. So it's not, yeah, it's kind of developed by H2O folks, but other people could contribute, and I think some people are contributing. Yeah, so it's open source.
I have a question.
Yeah.
So if it's open source, how do you guys make money, through consulting or what?
I don't think we are making money directly from data table, right? Maybe Pasha could explain this.
Yes, so this product is used in driverless AI, and driverless AI is a major money-making machine for the company. So as far as it works for driverless AI, we are making money off it, but we are also simultaneously giving it for free to anybody who wants to use it as well. So in that respect, we are not making money of it. So
you make money off licensing?
The license is free, so we are not making we are making money of it because we are ourselves using it, but we are not selling this particular software. This particular software is free for everybody.
So, how much is it different from Pandas data frame in terms of speed?
In terms of syntax, I think Pasha will cover this on the next slides. I just finished this part with machine learning and introduction, so you can easily just do pip install and get access to data table, check it out, and Pasha will make a real introduction to core capabilities of data table. Okay, thank you.
Yeah, okay, so my name is Pasha Stitsenko. I started working on data table at the same time that we started working on driverless AI product in the company. So how exactly did the idea of this product came out to be? So nearly 2 years ago, when we started working on driverless, we were considering what will be the platform for our new product, and we decided that the product itself will be written in Python. So one of the main feature is how we're going to handle the data, how we're going to store the data, how we're going to manipulate it, and so on. So, of course, primary contenders in that space are Pandas and NumPy, and everybody knows that. At least that was what was 2 years ago. But we quickly saw that this is not sufficiently good for us. Pandas is known to be not very fast and memory hungry, and this is especially visible when you are dealing with huge data sets, as we are dealing every day in driverless AI. So Pandas was out of the question, and then we knew that in R there is an excellent package called data.table developed by Matt Dowley and the team. That solves a very similar problem. The very similar problem that in R there is a data frame, built-in frame that is reasonably good and has many features, but it's memory hungry and it is not very fast. And which is why data.table in R was created to alleviate those problems. So we wanted to do the same thing for Python. Basically, we just said, okay, let's just do equivalent of data.table in R, but in Python. And everybody loved the idea, especially our host of Kaggle Grandmaster, who of course know everything about all the possible packages in all, both in R and in Python, and who often said to us, well, one of the things that we miss most from R in Python is the lack of data table package. So we started working on it. And what we wanted from that package is that first, that it would provide efficient data manipulation, and efficient meaning in the modern multi-threaded world, it should use all CPU cores to process the data, and it should also be memory efficient. Because we know from experience that if you take a small data set, say few gigabytes, and load it in Pandas and start manipulating in Pandas, quickly you'll end up using hundreds of gigabytes of RAM, and then you just run out of memory, and what do you do then? So we wanted to have as little memory footprint as possible. And we also wanted for it to be efficient in terms of disk access. So we decided that we are going to use memory mapped files in order to store data on disk and load data on disk and use the data on disk as if it was in memory, thus allowing us to quickly recover from errors and to allow to further parallelize any processing across different processes. As you might know, in Python there is no true multi-threading in the sense that there is this global, so-called global interpreter lock. That means that only one instance of Python can work at a time. Only one thread in Python can work at a time. So in order to fix that, there is a multiprocessing package that just spawns multiple Python processes that are independent system processes that work on the data simultaneously, but the problem then is how you handle data to that processes. And you want to do that in a way that that doesn't involve too much copying. Basically, you want to say, here is the data, work on it, without copying all those hundreds of gigabytes of data. And to do that, we use the memory mapped files. Of course, there are other mechanisms nowadays, like Plasma Store, for example, but essentially it is exactly the same. It's a memory mapping of files that are stored either in memory or on disk, or on Linux systems, disk and memory are essentially the same. in spirit of our data table, the Python data table package, we decided that it will be open source from the very beginning. So that was, we decided that we do not want to keep this to ourselves. We want this to be a platform that we will share. Okay, so let's start with looking how we're gonna work with the data. So the first thing that you usually do is you load data, and there is a fread function for that. It has the same name as in our data table. So this is just reading of CSV files. And here, here's how it will look in a Jupyter Lab. So we are looking at the frame, and it provides a nice view. You see columns are color-coded according to their types. And there are also little dots that show you how much data precision it is. Either it's 4 bytes per column or 8 bytes per column, or is it like a 1 byte per column, which if it's a Boolean column, so that you can quickly guess how much memory that particular column is taking. And for this particular data set, you can see that, well, we measured that this is like approximately 5 times faster than Pandas. We have different results. Sometimes it's more than 10 times. Sometimes it's like 2 to 3 times. But generally, it's way faster to read the data because we are using the multi-threaded reading of files. And fread was the first functionality that we developed in data table because, well, it is the first step that is needed for driverless to work on any data. You need to first load it, and the data usually comes in, well, not usually, but at least half the time comes in form of CSV files or other text files. So fread is a functionality that it is available in our data table, and it was used as a starting point of implementation in Python, fread as well. So it's a function that that is able to fully automatically detect parsing parameters. It is very robust in terms of recovering from encoding errors, processing multi-line files, and so on. So it's similar in a sense to Pandas read CSV. In Pandas read CSV is also very robust, but we found that some other newer packages, such as, for example, Dask, that also provide multi-node, multi-threaded CSV readings, they already lack robustness because whenever you try to parallelize it, you can run in all kinds of corner cases, and it is not very easy to recover from them. So fread is able to read the data with full robustness. And as an added bonus, it also reads Excel files, and it also reads archives. It also can go inside the archive and read a particular file in the archive. So this is just a very nice function that is useful in many ways. So the next thing that you do is we save it. So we always save the data to a binary file that we will later memory map because we want to access the data from multiple processes, as I mentioned earlier. So because each process will do its own set of munging, its own set of transformations, so that it can later on fit some kind of XGBoost model or some other kind of model on it. So in driverless AI, we have multiple processes that work on the same data at the same time, which is why we always read the data, then we save it into binary file, then we open that file in each processes and keep working. So saving, as you can see, we measured saving this file. It was only 300 milliseconds. So, and the file was 750 megabytes, or a little bit less than a gigabyte. So it's pretty reasonably fast, 2 gigabyte per second, and that's on a laptop. So on a server, you will see a better performance. And of course, all these writes are cached on an operating system level, so that you're not actually writing the data. You're just saying to the operating system that you should just write it at some point, and then operating system defers that to some later time whenever it finds a time. but we can use the data immediately in the processors. So whenever we say write the data, and then in the child process we say read the data, the operating system doesn't flush the data to disk and then pull the data up from disk. No, the data remains in memory, and then when you say open, that data just is taken from memory. It's not even copied, it's just taken from the pointer is created to the same virtual memory page. And which is why it takes almost no time for us to do this data passing from the master process that read the data to all the child processes. So as you can see, the timing here is 300 microseconds to open the file that was just created. Yes, a question?
Is it garbage collected?
The data? No, the files are not garbage collected. They are just regular files. So if you save it explicitly, you probably want to delete it later on explicitly, or not delete it if you want to keep it.
Yeah, but I mean, is there any real-time garbage collection loop running?
The data pointers that you created, like this DT variable, of course, as soon as this variable goes out of scope, the memory mapped file is closed and the memory released. So in that sense, there is a garbage collection only. Just not at the file level, it's at the Python level. Does that answer a question?
Well, I mean, if I grow a file or if I delete some temporaries, does it ever interrupt the latency of the processing?
So if you drop the variable and just reopen it again, then there is no difference really for you, because all the memory is still cached at the operating system level. So then whenever you say I want to memory map the same file, the operating system will already find those memory pages in memory and will just give them to you. So we do not touch anything in that level. Okay, so one other thing about data table is that it has a very interesting syntax, which is not particular Pythonic, but it will be very familiar to you if you used data.table in R. So in Python, we are using most operations we want to express in terms of these square brackets. Square brackets meaning like a selection of something, because we have data, which is a matrix, and we want to select data from that matrix. So the selector syntax is expected. And we also draw a parallel between that syntax that we use and the SQL syntax, which is also almost de facto standard for data manipulation, at least in databases. So the starting point of the syntax is this ij entries, where I means which rows you want to select, and j means which columns. And you can put many different things in that I and j. We'll look at that a little bit later. Just the same as you can put many different things in j and in I in a SQL statement. And then you also can put there a by clause, meaning that you do the same operation but in groups, by groups. And you can also add a sort if you want to maybe sort those groups or not groups if you don't have groups. All of these are optional, by the way. And then there is also a join, which could be a single join or multiple joins, where you could say, I want to join additionally a few other tables, and then maybe select or filter by columns in those tables as well. So here I and j could be a primary things that are rows and column selector, and all the others are modifiers that are optional. And the parallel with SQL syntax is that j, as a columns, is what we want to select, so it corresponds to the body of the select keyword. Then from dt is a data table from where we selecting. Then you can have, in SQL, you can have a join. And then you can have a where. In SQL, there are two keywords, where and having, which both tell you what kind of rows you want to select. And in our case, we have a single I, but that single I can select you both as where and as having. They're kind of versatile in that way. So if you primary difference in SQL when you're using where and having is that having will allow you to select something that is done post-aggregation after you did group by. So basically, if you saving having and you have an expression that you can use an expression that uses a group by column, for example. So in data table, you can use the same in I if you say that if you just use an expression that contains a group by column, that is exactly the same as if you were using having. So we are able to detect what your actual intent is, and filter the data either before or after the aggregation. So here's some of the examples. So this is the same data set. Assuming the same data set, flights data set that we loaded before. So the flights data set is basically the airlines flights. And we have some variables such as arrival time, departure time, flight number, and so on. So the first expression shows you how to find the average flight duration for each flight. So for each flight translates into a by clause, meaning that we are going to group by flight number in this case. So we are grouping by this variable called flight number. And then for once we did the grouping, we want to say, okay, so what do you want to do with each group? And here we say that the first column means that we do not do any filtering, and then the second expression shows us what do we want to do for groups, for columns. And for columns, we want to find the mean or the average of arrival time minus departure time. So arrival time minus departure time is how long it took for a flight to, for airplane to fly from the source to this destination. So we take the average of this, and this will give you the average flight duration for each flight. And it will return to you again a data table frame so that you can do whatever further processing you need. So this is the example of the data table that is returned in this case. And as you can see, it is grouped by flight number, and this column C0, which is automatic name for that unnamed column. We could have named that column, but we did not. So, which is why it was assigned automatic name C0, and this is a default. This is how long it took for it to the average flight duration. So the second example is. This time we are using joining and we're using filtering. So let me see. Okay, so we have so average flight is a table that was created in the first expression. So it is this table, and we're now joining it to the original flights table. So once we do the join, that table. Joining can occur if both tables are keyed by the same column. So in this case, we created the average flight table, and it was grouped. So we know that this is a key of that. This is a key of that frame, so that it knows that it can use that column to automatically match it to the original table. So it is called natural joining, and so we can naturally join this table, which is a transformed DT, to the original DT. So here we are joining it, and then we're saying that we're referring to that column, which is average flight duration, which is g.c0, and we're saying that, okay, find me the rows where that variable is negative or it is NA. So this is an example where it is NA, this is an example where it is negative, so presumably some kind of data corruption occurred. And then we are deleting that. So we're deleting those rows from the original table while at the same time filtering and joining. So this is a sort of power of the data table syntax that we can express so many operations in just a single expression. We are saying we are deleting, we are filtering, and we are joining, all in just a single expression that uses a uniform syntax. Right? So I don't need to memorize 3 new functions how to do that. In order how to delete something that is filtered and so on, in order to, like you would do that, for example, in pandas. And this is another example is how we can use a sorting at the same time as grouping and also filtering. So we are selecting 3 longest flights for each flight number. For each carrier. So we are grouping by the carrier, and carrier has multiple flights. Then we are also sorting by the flight duration, which is airtime column, and we are using minus to sort in the opposite direction. And then we're also filtering. This is column 3 is a familiar Python syntax, meaning select 3 first elements, but we are not selecting 3 first elements from the entire frame. Since we already have a grouping expression there, it means that we are selecting 3 first elements in the group. So we are saying that, okay, group by carrier, then select 3 elements in that group, in each group. So these I and j, when combined in a single expression with grouping, sorting, and joining, can provide as rich syntax as basically entire SQL, right? As was shown in the first slide. So
the sort minor side there is mean descendant, right?
It means descendant, and that actually internally. Data table looks at that minus, and it knows that it doesn't need to compute the minus of something. It knows that it's descending. So you can use a string column, minus string column there, and it will know that, minus of a string column doesn't make sense, but when applied to sorting, it will know that, oh, I need to sort that in descending order. Okay, yeah, so that was the last slide, and that was a brief overview of how we handle of what data table is and what its syntax is, and how we endeavor on this task of porting our data table to Python. And it's time for Q&A. Right, Alexi. Okay, now is the time for questions. Okay.
So it appears you have the same syntax for data tables being used in Python as in R?
It's as close as we could possibly match, given that they are really different languages, and some of the constructs that are possible in R are completely impossible in Python, and vice versa. So we are trying to mimic it as much as we can, but sometimes we cannot. So, but we're trying.
Have you run comparisons between your data table and the data table in R against similar size objects?
Comparison in terms of speed, we have at least some benchmarks that are developed by one of our colleagues, Jan Gorecki, and he runs. He developed this benchmark for things like grouping and sorting, and also I think recently he started working on data reading as well. So data table compares pretty well against data table. I mean Python versus R. So for some operations we see that Python does a little bit better. For other operations R does a little bit better. So we're trying to reconcile those differences and see where we can improve both on both sides. So it's a process ongoing, but it compares pretty well against definitely against the pandas, for example, and other packages that we tried. Yeah.
Which OR syntaxes can you not implement in Python?
Which syntax is not implemented?
What are the main features that we...
Yeah, so one of the main features that we have not gone to implementing yet is this .sd syntax, if you know. It's when you apply arbitrary function to each group. So we have not gone that way yet, but we have some ideas, and we have at least a blueprint of how we're going to do that. So we just haven't had a use case where we really needed it. So it got a little bit down prioritized, but we think that we should be able to get a feature parity eventually.
And you can do inline mutation like in R?
Yeah, absolutely. So you can, I don't know if I have that, I don't have that example yet, but basically in Python, you can have square brackets, and then you can have a square bracket assignment, right? So you can you know that you can say to this slice assign me something. So that's a built-in Python syntax, and we also use it in data table as well. So for this expression, I guess I should have written that equals anything, and that equals anything will also be handled. Just like you can say del this thing. So if you put a delete operator there, then it will try to delete whatever you're referring to, if it makes sense. So the assignment, yes, it is handled, and you can, and it will do inline mutation with as little copying as possible.
So your SQL engine, I'm here. Your SQL engine that you're really using to manipulate data on, is it an open source that you borrowed from somewhere, or is it like from scratch, or how would it be different from Oracle's SQL or some other?
Well, this is not a SQL engine per se. This is just analogy with a SQL language that we are using here. So the engine that we're using is written by us completely from scratch, essentially, and it is similar but not exactly the same as in SQL. For example, in SQL there is no notion of row numbers. So in a question such as select me 3 first flights for each carrier would just make no sense, because there is no first anything in SQL. I mean, unless you have row numbers and then just sort by them. But it would be difficult to express that in SQL. How to select first 3 something by group, for example. So it's not the same. It definitely not the same engine. And in terms of functionality, the SQL of course has something that we are not offering. They have grouping sets, multiple grouping sets. They have rolling windows that we do not have yet, by the way, and our data table. That's another feature that our data table has, and we don't have yet. The rolling windows, some other things, perhaps. So.
And then what about the optimization? Like how SQL engine really optimized the query for forward scan and backward scans?
Yes, so we do have some internal optimizations. We optimize for speed, and we are offloading everything to our parallelized engine internally to process the data, column by column, and then in chunks of rows in parallel. We do some merging of some operations. So if this is on ad hoc basis, but basically we know that some operations can be combined, like sorting with grouping, and extracting a subgroup from a sorted set and so on. So some of those that we know of, we optimize and defer to a different implementation. But otherwise, we just run whatever you give us.
And then how long did it take you to develop the whole product? As of now, like 5 people for 1 year, or 2 years, or 3 years?
So we started 2 years ago in March. So that's 2 years and 3 months. And at first I was by myself on the project, and then Alexei joined how long ago?
1 year ago.
1 year ago, yeah. So it's still work in progress, very much, but this is a project that is used in driverless AI in every day, so it works, at least in that sense. Yeah.
So you store the file in a binary format. Do you add some extra encoding, or you just directly write the?
Yes. So we are. Basically, it's as little encoding and as little compression as possible, so that we can memory map that file and use the data directly. So we have started talking internally about adding possibly some optional compression, so that the data can take a little bit less memory both on disk and when loaded in RAM. But at least for now, it is uncompressed. So if you have a million of doubles, it will take exactly 8 million bytes.
Thank you. Yeah.
Anything else? All right. Well, then thank you very much for coming, and enjoy the pizza and the rest of your day. Thank you.